Good day everyone. So for today's video, let's talk about the security best practices for big data solutions of Google. Safeguard distributed programming frameworks. To begin, create trust by using methods like Kerberos authentication and ensuring that predefined security policies are followed. The data is then de-identified by decoupling all personally identifiable information from it, ensuring that personal privacy is not jeopardized. Then, using mandatory access control, such as the Sentry tool in Apache HBase, you allow access to files based on predefined security policy and ensure that untrusted code does not leak information through device resources. After that, the hard part is done. All left is to maintain the system to prevent data leakage. In a cloud or virtual environment, the IT department should be scanning worker nodes and mappers for bogus nodes and altered duplicates of results. Next is secure non-relational data. Non-relational databases such as NoSQL are common, but they're vulnerable to NoSQL injection attacks. By encrypting or hashing passwords and maintaining end-to-end encryption by using algorithms such as Advanced Encryption Standard or AES, RSA, or Safe Hash Algorithm 2. Next is secure data storage and transaction logs. Storage control is a critical component of big data reliability. By using signed message digest to have a cryptographic identifier for each digital file or record, and to use a technique known as a Secure and Trusted Data Repository or SUNDR to detect unauthorized file modifications by malicious server agents. Next is endpoint filtering and validation. Using a mobile device management solution, you can use trusted credentials, perform resource verification, and link only trusted devices to the network. Using statistical similarity detection and outlier detection strategies, you can process malicious input while defending against cyber attacks. One person posing as several identities and ID spoofing attacks. Next is real-time compliance and security monitoring. Organizations can use techniques like Kerberos, SafeShell, and Internet Protocol protection to get a grip on real-time data by using big data analytics. It's then simple to monitoring logs, set up front-end security mechanisms like routers and server-level firewalls, and start putting security controls in place at the cloud, network, and application levels. Next is preserve data privacy. Employee awareness training centers on new privacy laws and ensures that information technology is kept up to date by using authorization processes. In addition, data leakage from different databases can be regulated by analyzing and tracking the infrastructure that connects the databases. Big data cryptography. Mathematical cryptography has improved significantly. Enterprises can run Boolean queries on encrypted data by creating a method to scan and filter encrypted data, such as the Searchable Symmetric Encryption or SSE protocol. Granular access control. The two main aspects of access management are limiting and allowing user access. The key is to create and execute a policy that automatically selects the best option in any given situation. Granular auditing. In big data protection, granular auditing is essential, particularly after a system attack. Organizations should develop a unified audit view following an attack and include a complete audit trail with quick access to the data to reduce incident response time. The integrity and security of audit records are also important. Audit data should be kept isolated from other data and safeguarded with granular user access controls and routine reporting. Data provenance. It's provenance metadata that big data applications produce. This is a different kind of data that requires special protection. Creating an infrastructure authentication protocol that manages access and sets up daily status alerts and constantly checks data integrity with checksums.